Did you know that subtle changes in the brain, such as the enlargement of small spaces around blood vessels, might be linked to catastrophic diseases like Alzheimer's and dementia? To understand this, imagine your brain as a vibrant complex city. Just like the city needs pipes and sewers for the water flow, the brain has perivascular spaces, or PVS. They act as the brain plumbing network, facilitating the flow of cerebrospinal fluid, or CSF, which is critical for waste clearance throughout the entire organ. Here's an illustration of what an actual PVS looks like. But when you look at them in real MRI scans, these tiny structures have such low intensity and subtle contrast that they're barely visible to the naked eye, making them incredibly difficult to measure and quantify accurately. This difficulty is what prevents us from using PVS size as a reliable early biomarker for disease progression. To quantify this PVS, we have two main paths in medical imaging today. First, the traditional numerical approach, like Haitian filters. The most famous being the Frangi filter and being the subject of this research. The pro is that they have solid mathematical foundation. The cons? They suffer from extreme parameter dependence, and in the case of Frangi filter, it's very sensitive to noise. The second approach is the deep learning models. They have high accuracy potential, but they have severe cons. We need enormous, perfectly labeled datasets. Access to real high-quality MRIs is already complex, and it's even harder to get large amounts of data that have been manually annotated by clinical experts. So we return to the robust, mathematically grounded Frangi filter. Its major weakness, the one we are tackling in this research, is the selection of the scale parameter, represented by sigma. This scale sets the sensitivity of the filter to specific size details. Choosing the wrong scale can completely ruin the segmentation, regardless of the image quality. Take a look at this example. If the scale is too small, the filter sees nothing but noise between the PVS. If the scale is too large, it blurs the PVS and highlights massive irrelevant artifacts. Only when you hit the optimal scale does the filter accurately maximize the PVS contrast. This scale is the single most critical and ambiguous factor that determines the successful quantification of PVS. The optimal scale should not be a constant. It's a dynamic variable controlled by the physical characteristics of the MRI. The first factor is the image quality, primarily measured by the signal-to-noise ratio, or SNR. This ratio measures the proportion of signal intensity, in this case of the brain tissue, against the noise standard deviation caused by the random electrical interference. But how does noise affect the scale? The visibility of tiny structures like PVS heavily depends on the clarity of the image. Basically, as the image gets noisier, that is, the lower the SNR, the bigger the optimal scale must be. Why? Because a larger scale forces the Frangi filter to smooth out noise while still attempting to capture the PVS, which now looks slightly broader due to the noise blur. The second factor is the image resolution, defined by the voxel size. As PVS are the smallest structures we're trying to measure, the size of each cubic volume element, the voxel, determines the minimum detail the image can capture. Traditionally, the Frangi filter has been applied using default fixed scale parameters, a guess essentially determined by a radiologist or a technician. This is not the best way to do a scalable, reliable analysis. We need an intelligent, automated solution. Introducing SCALR. SCALR automates the entire process of selecting the optimal scale for each individual image based on its quality. The goal is simple. Take the two measurable features, the SNR and the voxel size, and predict the optimal scale for that specific image. To train SCALR, we needed a robust dataset covering every possible scenario. We used three groups: real denoise MRI for ground truth morphology, synthetic MRIs generated by a specific PVS framework for perfect masks, and most importantly, hybrid images, where we took real images and systematically introduced varying levels of noise and resolution changes. This taught the model how to distinguish signal from noise across different hardware configurations. But how do we define what an actual optimal scale is? Well, for every image, we tested the Frangi filter across hundreds of scales, from 0 to 2.5 millimeters. The optimal scale was defined as the one that maximizes the contrast between the PVS itself and the small boundary shells surrounding it. This process gave us a target scale for the model training. The relation between SNR, voxel size, and scale is complex and highly nonlinear. A simple linear model would fail. Therefore, we developed SCALR as a multiple linear regression model that utilizes a polynomial feature transformation of third degree. But what does this mean? We take our two features, square them, cube them, and create interaction terms. This turns the underlying linear regression into a powerful tool capable of fitting this complex curved surface that you see here. When we plot the noise level and the resolution versus the scale annotated by our dataset. All the points that you see here represents actual optimal scales for each image with its own measurement. And the polynomial fit is the function that satisfies most of the points in the dataset, making a continuous function that can be applied to any type of image resolution and noise level. And the results confirm its performance. The model achieved a remarkably low mean square error of 0.01 and a strong R-squared score of 0.80. And R-squared over 0.8 means our two input variables, noise and resolution, explain over 80% of the variation in the optimal scale parameter. Most importantly, when we tested SCALR on unseen MRIs, the predicted scale consistently produced segmentation that closely aligned with the manually determined optimal scale. This visual proof confirms that SCALR correctly identifies the true scale required to maximize PVS visibility for segmentation. In summary, SCALR solved the single largest ambiguity in traditional PVS quantification, the scale selection problem. By using objective, measurable image quality features, SNR and voxel size, we provide a reliable, scalable, and automated solution that can integrate Frangi-based PVS analysis into clinical and research workflows with greater confidence, particularly in low-quality MRI environments. Before concluding, we must express our sincere gratitude to our funding partners and data providers. We acknowledge the support of the Gallen and Hillary Weston Foundation and the Rolf Fogel Charitable Trust. Furthermore, the valuable real medical image data utilized in this study were generously provided by the DCNE. Thank you for your attention. I am Juan Diaz, and this is SCALR, a medical tool we hope will contribute to more robust and automatic PVS research.